Alright, we're in unit number 6, and in this particular video we're going to define power, tell you about power, and work you through basically an equation or two. So we're going to start right at the top, give you two definitions of power. The first one I'll give you is more, I guess, more of a technical definition. The second one is more, I think, more of a layman's definition, but here we go. Power. This is the rate. So when we think of rate, we want to think about how fast you do something, which is going to be basically what we're going to have in number 2. So it's basically how fast. So the rate at which work or energy transfer. Remember that work is the same thing as transferring energy. So anytime you transfer energy, you're doing work. So the rate at which work is done, or the rate at which energy is moved from one form to another, or the rate at which energy is moved from one object to another. Another way of saying that is how fast work is done. So if you can't read it right there, it says how fast. So when you think of power, you want to think about how fast something's done. If you know someone who might be lazy, they're not very powerful. Someone who gets a lot of stuff done in a real quick time, they're powerful. So power is how fast you get something done. It's power. All right, we have two equations. The first equation I'm going to give you is kind of a fancy one. It's one that we won't use too often, but we're going to use it to get to another equation here in just a moment. All right, so power is really the dot product between the force you exert and how quickly you're moving, or the object, or whatever it is that you're doing. It's how quick. So if it's a dot product, then we can also define it as FV cosine theta. Remember that anytime you have a dot product, you can redefine it that way. Just remember that at the beginning, and these are vectors, and down below we take the vectors off and just use the cosine part. Okay, so this is one equation that we can use. Let's use this to determine the units of power. So the units of power, force is measured in newtons. V is measured in speed, so that's going to be newtons times meters over seconds. Well, we know what a newton meter is, so a newton meter is a joule per second. So we measure power in joules per second. We give that a name. Joule per second is also known as a watt. All right, we can also break this up a little bit more. A newton is, let's see, a newton, that's going to be a kilogram meter per second squared. Make sure I can do that so you can read it. And then we're going to multiply it times a meter per second. So if I multiply the meters together, I get a kilogram meter squared over second cubed. And so power is a joule per second, it's a watt, and it's also a kilogram meter squared over second cubed. So if we go down below and we look at this next the second bullet point down here, we can fill this out. So record power on your dimensions in unit sheet. Include the most common unit. The most common unit for power is going to be a watt, and then all the equivalent units. So the equivalent units are going to be a joule per second, and also a kilogram meter squared over second squared. All right, and we don't need these two right now. So the governing equations: F equals F dot V. Now that's not the one we're going to use most often. We're going to come up with another one in just a moment, but that one is probably, in terms of technical use, that one's probably the best one to use. All right, so we're going to go back over and look at this next equation a little bit more. So I got power is equal to F dot V. Well, all right, that works, but let's go ahead and redefine it as FV cosine theta. And then let's break up this V. We know that V is going to be distance divided by time. And then I can play with this a little bit. I also know then that F times D is work. And we kind of just drop this off here, and we just focus on this. So power is going to be work divided by time. And when you hear power, most physicists generally use work divided by time, especially here at the high school level. So power is also equal to work divided by time. And let's go back over here and I see a mistake. So I just put in power is equal to work divided by time. And power is also, I think I had an F here earlier. So power is equal to force dot is the velocity. All right, and the one we're going to use most often is this guy, although this one does show up from time to time. All right, we also need to know a key conversion, and 1 horsepower, which is going to be HP, that's the abbreviation, is equal to 746 watts. So we can actually come back up here and add in HP as another unit for power. So we have two kind of units for power. We have watts, we also have horsepowers, but they're not equivalent. So it takes about 746 watts to equal 1 horsepower. Okay, the next part, key concepts. So you've heard of power before, and you've probably heard of it with light bulbs. So the next question would be, well, what does it mean that a light bulb has, or is rated at, 100 watts? What does that mean? So what does it mean when a light bulb has a rating of 100 watts? Well, it means this. 100 watts, but we know a watt is the same thing as a joule per second. So that means it's giving off 100 joules of energy per second. So hopefully 100 joules of light per second. We now know that it's not necessarily going to be 100 joules a second. Sometimes it's going to be giving off a little bit of thermal energy, but basically it's doing 100 joules of work every second, or it's giving off 100 joules of energy every second. How come a 100-watt light bulb will shine brighter than a 60-watt light bulb? Well, a 100-watt light bulb is giving off 60 joules every second, while a 60-watt light bulb is giving off only 60 joules per second. So this is giving off more light per second than this guy. And that's power. When we come back on the next video, actually, no, I'm not done. I have to go to example 3 and finish this off real quick because now we know power. So let's go to example number 3, which is on the previous page. And on example number 3, we've got, adjust this real quick. All right, example number 3, it says calculate the power needed to raise the apple 1 meter in 1 second. So on a previous video, I think we had an apple that weighed 1 Newton, and we lifted it 1 meter in 1 second. Now what we're going to do is we're going to calculate the power that was exerted to be able to lift that apple 1 meter in 1 second. So we're going to start off with, I think, the simpler equation, and that's power equals work divided by time. And so I need to know the work, and I need to know how long. Well, I already know how long because I did it in 1 second. To know the work, I need to go back up to part B up here. Part B, right here, said that we did 1 joule of work in this part. So I'm going to go ahead and transfer that down and do 1 joule of work, and I can do that math in my head, and that'll be 1 watt. So to lift 1 apple 1 meter in 1 second takes about 1 watt. Okay, the next one, we're going to do the same thing, but we're going to use the other equation. So this is going to be power equals force dot V. And we'll kind of throw this in as we go along. So we've got power is equal to force times speed times cosine of the angle between them. So power is equal to the force. Well, what force were we exerting? You remember that? If we go back up to, we'll see, which one did we do that on? I guess we can use this one. Yeah, here it is. Bullet point. When lifting an object at a constant velocity, which is what we did, the upward force equals the weight of the object. Well, the weight of the object was 1 Newton. That was the weight of the apple. So if you lift the apple that weighs 1 Newton, and you lift it at a constant velocity, then that upward force is also 1 Newton. So I'm going to go 1 Newton here. And then the speed, well, if I lift it 1 meter in 1 second, that's 1 meter per second. All right, now let's do the angle. The angle is going to be between the force and the speed. Well, if I push up on the apple and the apple's moving up, both of those are up, and so the angle between them are going to be 0 degrees. So this is cosine of 0 degrees. And if I plug all that into my calculator, it'll give me 1 watt. And look at that. It's the same thing. It should be 1 watt. It should get the same thing regardless of the equation that we use. All right, let's finish off letter I. The work done by you on the apple will blank if the apple were lifted in twice the time. So if we lift it in twice the time, what's going to happen to the work that we do on the apple? Well, let's remember a little bit. Work was, let's see here, work was F dot D. Notice that there's nothing here about how long it takes, like time. So how long you do it, how long it takes you, has no bearing on your work. How long it takes you affects your power. So the work done by you on the apple will remain constant if you take twice the amount of time. However, now look at the letter J. It's a different question. The power generated by you will, what will happen to it if the apple were lifted in twice the time? Well, if it takes you twice the time, that means it takes it longer. And if it takes it longer, you're not exerting as much power. I almost said working is hard, but that's not true because you're working the same amount. But you're not exerting the same amount of power. So the amount of power that you exert will go down because it's taking you longer to do that same amount of work. And then letter K, how many apples will you need to lift 1 meter 1 second to produce 1 horsepower? Well, if we go back to the previous page, we found out that 1 horsepower is 746 watts. So if you want, let's see, if you do to lift 1 apple, it takes you 1 watt, and you want to do 1 horsepower, and 1 horsepower is 746 watts, then you're going to have to lift that apple 746 times, or you're going to have to lift 746 apples 1 meter in 1 second. Either way, but that's a lot of work to be doing. So there it is, and our next video will be on page 8, and we'll take a look at inclined planes.